Hi everyone and welcome to today's video. Today I'll be introducing another method of integration. So the method is integration by parts. How does this work? Find out in today's video. Okay, integrating by parts. So this is the next section. Now this is a method that we're going to use, especially if you've tried substitution method on a number and you've seen that it won't work, or if you've also tried sign substitution and you've seen that it not work. Integrating by parts can be another method that you can actually try out. So this method is used especially to integrate a product of two functions, where one is a polynomial and the other is not, or where both functions are not polynomials. So this is why you use integrating by parts. So if u and v are functions of x, then we're saying d dx of uv of the product of uv shall be equal to u dv dx plus v du dx. So putting integrals on both sides with respect to x gives uv being equal to integral of u dv dx plus integral of v du dx. Then as you can see, if we make the integral of u dv dx, this the subject, we shall have it being equal to uv minus the integral of v du dx, as you can see right there. So basically this is the formula that you need to memorize and have at your hand at all times, because this is what's going to help us to solve all the different numbers in this section. Let's look at an example. So in this question we're being told to find the integral of x cos x. As you can clearly see already, sign substitution will not work on this number because we have an x which is a different function from cos x, so we cannot use sign substitution on such a number. And then we can also see that this is a product of two different functions, the x and the cos x. So this is clearly a number that's going to need integration by parts. So what are we going to do? So this is what we have. So we're going to let u to be x, then we're going to let dv dx to be cos x. So that's what we're always going to do. You're going to let one of the values to be u, then you're going to let the other value to be dv dx. And then using that knowledge, we're going to, so on this side where you let u to be equal to x, we're going to differentiate that. So in differentiate this, we'll get du dx as being equal to 1. And then on this other side where we have dv dx, we're going to integrate this term right here. So we need to find the value of v, but we can only find the value of v by integrating the value that we made to be dv dx. So we're going to integrate cos x, and then when we integrate that, we can see that the integral of cos x is sine x. So v is going to be equal to sine x. So now that we know that, in integrating by parts, we're going to remember the formula is written like this. So what we're going to do is we're going to substitute in the value. So where there is u, we're going to put an x, and where there is dv dx, we're going to put in cos x dx. As you can see, when you substitute in all the terms, this value on the left hand side looks like that. Then where there is uv, you know that u is actually going to is x, and then v is sine x. So that means we have x sine x, as you can see right here, minus the integral of, remember that v is sine x, and then du dx is 1. So it's like 1 times sine x, which is actually just basically sine x dx, as you can see right there. So this is what we get by putting it there. But as you can see on this side, we have to find the integral of sine x, which is again negative cos x plus c. But remember, because there's a minus sign here, it affects this minus sign and we'll have a positive. So therefore our answer shall be x sine x plus cos x plus c. And this is our answer to the integral. Alright, so question number 2, we're being told to find the integral of x sine x cos x dx. Now this looks slightly different. It's because it seems we actually have three functions. We have x, we have sine x, and we have cos x. Now this we'll have to do something like this. We'll have to reduce this to two different functions. We can't have them as being three different functions. But good enough, the knowledge of trigonometry can help us combine the sine x and cos x together by remembering something. So from trigonometry, we remember that sine 2x is equal to 2 sine x cos x. As you can see, we have sine x cos x right here. So what that means is that if we make sine x cos x a subject, it shall be equal to a half sine 2x. So this is actually a better way of expressing that. So we're going to replace sine x cos x with a half sine 2x. Alright, so now we have a half sine x sine 2x dx. So what we're going to do is we're going to let u to be equal to a half x, and we're going to let dv dx to be equal to sine 2x. And then there we can already say that du dx, which is the derivative of a half, x shall be equal to a half. And then when we look at the side where there is dv dx, if we want to find v, we're going to have to integrate sine 2x. So if we integrate that, we're going to get negative a half cos 2x as our answer for v. And then now we can apply the knowledge of integrating by parts. So inside this formula, we're going to substitute in the values. So this is what we have on the left hand side when you substitute in the values. And then remember that u is a half x times v, which is negative a half cos 2x, and that's why we have it looking like that, minus the integral of, so where we have v remember is negative a half cos 2x times du dx, which is equal to a half. So we have that times a half dx. So when we multiply those, we'll end up having, so for each group we'll have negative a quarter x cos 2x plus, as you can see here already, this negative sign is going to be affected and we're going to have a plus. So a half times a half is a quarter. So we're going to have a quarter outside the integral of cos 2x. Now what do we get when we integrate cos 2x? We actually get a half sine 2x. So a half sine 2x, so a half times a quarter is going to be 1 over 8. So we have 1 over 8 sine 2x plus c. So this is our final answer right here for this integration number. Alright, let's move on to another question. So question number 3, we're being told to find the integral of tan inverse of x dx. Now this does not look obvious from the very start, as someone may see right now, but actually this is an example that also require integrating by parts, because we can actually not use any other method directly. So when you have such a number like this, we shall just have to integrate by parts. What's going to happen is we're going to assume that, because right now we only have tan inverse of x, so what we're going to do is we're going to assume that the other function is 1, because 1 times tan inverse of x is actually tan inverse of x. So we're going to assume that the other function is 1. So what we're going to do is we're going to let u to be equal to this tan inverse of x, and we're going to let the other value dv dx to be equal to 1, because we're going to assume that 1 is the other function. So the derivative of tan inverse of x is actually going to be equal to 1 over 1 plus x squared. And then now actually in this case we actually have to be very, very wise. It is very wise that we did not let tan inverse of x to be equal to the value of dv dx, because if we try to integrate tan inverse of x, it will be taking us back to what we were actually trying to accomplish in the first place. So it's why we did not let dv dx be equal to tan inverse of x. So what happens is in some cases you actually have to just be wise in your selection, so that there is actually no form of repetition. So it was wise to actually make u to be tan inverse of x, so that we just find the derivative of it, then integrating it again. And then from here we can actually see that v shall be equal to the integral of this 1 dx, of which v shall be equal to x as the integral. So now from integration by parts, this is our formula. We're going to substitute in the terms. So the integral of tan inverse of x dx shall be equal to, so this is our values for u. u remember is tan inverse of x, and then v is x. So x times tan inverse of x, that's why we have x tan inverse of x right there, minus the integral of, so where there is v is x times du dx, which is this, as you can see right there. So when we do that, we'll have x tan inverse of x plus the integral of x over 1 plus x squared dx. Now after we've reached this part, we can actually see that this part here still needs to be integrated further, because we still don't have a final answer. But as I can already clearly see, this is a number that we can clearly solve by, so this side of it can be solved using substitution or u substitution. So what we're going to do is, for this section we're going to use u substitution for this part. So we're going to let u to be equal to 1 plus x squared, of which du dx shall be equal to 2x, and then if we make dx subject, dx shall be equal to du over 2x. So substitute that back in and we have x over u times du over 2x. So good enough, this x shall cancel, then we'll be left with this. So we can pull the half outside, and it will be a half into the integral of 1 over u du. Now the integral of 1 over u is ln u, so we have a half ln u plus c. So we're going to substitute that, but before we do that, we know that u is equal to 1 plus x squared, just as we had stated right here. So we're going to put everything back in terms of x. So now we're going to have it as a half ln 1 plus x squared plus c. So now then the integral becomes so the integral of tan inverse of x dx shall be equal to x tan inverse of x minus a half ln 1 plus x squared plus c, and this is the answer we're looking for. So in question number 4, we're looking at another unique example that is actually clearly similar. Now this is a number that clearly we can't use substitution, we can't actually use any other method. So we're being told to integrate ln x. Now this clearly will require us to integrate by parts. So just as we've done in the former number, we're going to assume that the other function is also equal to 1. So it's going to be like 1 times ln x. Of course we know that it will give us ln x, but in this part we also have to be wise. So it's going to be wise to actually make ln x to be equal to u and not let ln x be dv dx, because that will actually just bring about repetition. Because if we made it to be the value, if we made dv dx to be equal to ln x, we'd actually be integrating that again, and it will just take us back to what we're trying to accomplish in the first place. So the wise decision to do is to make u to be equal to ln x, and we're going to let the 1 to be that dv dx. So very many cases in integrating by parts, we actually have to be wise in our choices. So du dx shall be equal to 1 over x, and then when we integrate this, so to find v, we're going to integrate 1, so v shall be equal to x, as you can already see. So by integration by parts, we're going to substitute everything into the formula. We can actually say that the value of u is ln x, the value of v is x. So substitute that in, and we have x ln x minus the integral of, so v is x times 1 over x dx, as you can already see there. So this and this shall cancel, and as you can see, we'll just be left with the integral of 1, which the integral of 1 is x. So that's why we have x ln x. Now because of this minus sign, we're going to have a minus to that x that we shall get from this integral plus c, and this is the answer. So this is the answer for the integral of ln x, and that's the answer we're looking for. Alright, so moving on to question number 5, we're being told to find the integral of x log x base 10 dx. So this is another example of a number that actually will require us to use integration by parts. So what I'm going to do in this question, so this is what we have. So let's first consider that x log x base 10. So let's do something about it. So as you can already see that this value here, so we're going to actually express it. So we're going to try to convert this log, we're going to convert this in terms of ln. But remember that a ln is actually a log to the base e. Now log x to the base 10 can be expressed as log x base e divided by log 10 base e. So it's exactly similar to that. But remember that log x to the base e is actually ln x, and then log 10 to the base e is actually like ln 10. So that's what we have right there. So now we basically have x ln x over ln 10. So this is now how it looks in a more simplified version. So x log x base 10 dx shall be equal to the integral of x ln x over ln 10 dx. But in this case, we can already see that 1 over ln 10 is actually a constant, so we can actually pull that out of the integral, and then in the integral we'll be left with x ln x dx. Alright, so now that means we're going to apply integration by parts for this side of the integral. So what happens is we're also going to have to be wise with our selection. So I wouldn't want us to take a long process. We're going to let u to be the ln x, and we're going to let dv dx to be equal to x. So that's going to be a wise decision, because doing it otherwise would actually make the process more complicated, or actually impossible. So we always make u to be actually equal to the version that is more complicated to actually work on. So we're going to let dv dx to be equal to x in this case. So now definitely here the derivative of u shall be equal to du dx shall be equal to 1 over x, and then from here to find v shall be equal to the integral of this x dx, and then v shall be equal to x squared over 2, as you can already see. Therefore, integrating by parts, in the formula we're going to substitute in the values. Now remember that we already have this constant on the outside of the integral, so we'll actually have to remember that. So we're going to have this constant on the outside, then we're going to put all the rest inside a bracket. So it's going to be 1 over ln 10 into bracket. Now our u value, so our uv values are, so remember we let u to be ln x, and then this was the value we got for v, so it's x squared over 2 times ln x minus the integral of, now here we have x squared over 2, which was the value of the v that we got, times now du dx was actually 1 over x, then dx right there. So as you can already see, this and this reduce and we'll be left with the integral of x over 2 right here. Then here we'll have x squared over 2 ln x, and then this is what we have right there. But now we can see from here that actually you can pull out a half from this integral, and then we'll be left with having to find the integral of x, which is actually easy to work on. So therefore we'll have 1 over ln 10 into a half x squared ln x minus, as you can already see here, that the integral of x is actually x squared over 2, of which that a half that we get from it can multiply this a half, and that's why we have a quarter. So we have a quarter x squared plus c, and this is our final answer. So moving on to another question. So this is question number 6. So we're being told to find the integral of x sine inverse of x dx. Now when you look at this number, you can clearly see that we cannot integrate directly with any other method. So substitution method can also not work, or any other method as of sort. So we are clearly going to use integration by parts again. So we have two functions. So one of the functions is x and the other function is sine inverse of x. So we're going to let u to be equal to sine inverse of x, and I believe that is going to be easier to work on. So what happens is every time make u to be the value that is slightly more complex, and then dv dx shall be equal to x. So we can see that du dx shall be equal to, because the integral of sine inverse of x is 1 over root of 1 minus x squared, and then from here we can see that v is actually the integral of x, so which v shall be equal to x squared over 2. So integrating by parts, this is our formula, and then our formula is going to give us this. So we'll have, so our value of u, remember, is sine inverse of x, our value of v is x squared over 2. So we have them multiplying each other, and this is what we have, minus the integral of, so this side we have x squared, because v is x squared over 2, times, then du dx is this. So we're multiplying that right there. So what do we end up with? We end up having x squared over 2 sine inverse of x minus, as you can see from here, we can actually pull out a half. So inside the integral, we'll be left with x squared over root of 1 minus x squared dx, as you can already see there. Alright, so when I look at this integral right here, I can see that this integral will actually require us to use sign substitution to solve this side further. So let's consider this integral right here. So we have a half into the integral of x squared over root over 1 minus x squared. So this is going to clearly require sign substitution. So by sign substitution, we're going to let x to be equal to sine theta, as you can already see there. And then dx theta shall be equal to cos theta, of which if we make dx subject, dx shall be equal to cos theta d theta. So if we solve for theta, remember theta shall be equal to sine inverse of x, as you can already see from here. So therefore, when we substitute everything back, we'll have x squared over the root of 1 minus sine squared theta times cos theta d theta. But remember that now we can also put this in terms of theta. So we need to put x squared in terms of theta. So remember, we've seen that x is sine theta. So that means x squared is equal to sine squared theta. So we're going to make this sine squared theta, and we're going to put that right there. But remember that 1 minus sine squared theta is actually cos squared theta. But putting this in a root, we'll actually have cos theta. So this and this cancel, and we'll be left with a half into the integral of sine squared theta d theta. Now, this is an example where there is even powers of sine theta. So remember, from even powers of sine theta, that sine squared theta is equal to a half into 1 minus cos 2 theta. So this is very, very key. So we shall have a half into the integral of a half bracket 1 minus cos 2 theta d theta. Now we can pull out a half, and we'll have a quarter into the integral of 1 minus cos 2 theta d theta. So when you actually integrate that, we will have a quarter into theta minus a half sine 2 theta, of which when we multiply the quarter inside, we'll have a quarter theta minus 1 over 8 sine 2 theta plus c. So this is what we have. But remember that sine 2 theta can actually be represented as 2 sine theta cos theta, of which this 2 and this 8 reduce, and we'll be left with a quarter sine theta cos theta plus c. But now we remember that we cannot leave the answer like this, so everything has to be put back in terms of x. So what we remember is we're going to actually put sine theta cos theta in terms of x, because we already know that theta is sine inverse of x. So now we have to put sine theta and cos theta in terms of x. So we've already seen that sine theta is actually equal to x. What that means is we can also say that sine theta is x over 1, because x over 1 is the same thing as x. So now we're going to use this to put this on a right angle triangle, which will clearly show us that if we're looking for where the angle is theta, it means that the opposite is x, and then it means that the hypotenuse is 1. So now what happens is we actually have to now find the value of the adjacent, so that we can actually find what cos theta is also equal to. So from Pythagoras theorem, we know that a squared plus x squared is equal to 1 squared. So if we make a squared the subject shall be equal to 1 minus x squared, then a shall be equal to root of 1 minus x squared. So therefore it means that cos theta, remember cos is actually equal to adjacent over hypotenuse. So it means that cos theta is root of 1 minus x squared over 1. So therefore in our formula, wherever there is sine theta, we're going to actually put an x, and then where there is cos theta, we're going to put the root of 1 minus x squared plus c. But also remember that sine theta, this theta here is actually sine inverse of x. So we have a quarter sine inverse of x minus a quarter x root of 1 minus x squared plus c. So now that is what we get for this part of the integral. So now remember, now we have to go back to the initial full integral. So therefore the initial integral becomes integral of x sine inverse of x dx shall be equal to x squared over 2 sine inverse of x minus into bracket a quarter sine inverse of x. So we have to put this in bracket to be careful because there is a negative sign right there. So we now put this term in bracket, and then therefore if we open the brackets, we'll have this. So this becomes a minus and this becomes a positive. So therefore we can actually see already that we can actually combine some of the terms already. So as you can see from this group right here, the x squared over 2 sine inverse of x minus a quarter sine inverse of x, you can see that I can choose to factorize out a quarter sine inverse of x. So if I do that, I'll be left with 2x squared minus 1 in bracket, because when I multiply this back in, it will give me back these two individual groups of functions. So now this is the simplest way of expressing your final answer. Alright, so next question is a question from UNEB 2019, and this was question 16a. So being told to find the integral of ln x over x squared dx. So this is actually also a number that actually requires integrating by parts, because we cannot use NAU substitution. We can actually not even use trigonometric substitution. So this clearly needs us to use integration by parts. So now what we're going to do is, like we've done before, we're going to let u to actually be equal to the more complex value among the two. So u is actually going to be equal to ln x. But remember that we have, so this is the same as a quote 1 over x squared times ln x. That means dv dx, it shall be equal to 1 over x squared, which is the other function. So the two functions are 1 over x squared and the other function is ln x. So dv dx shall be equal to 1 over x squared. Now from here we can see that du dx shall be equal to 1 over x, and then therefore v, we're going to find v by finding the integral of 1 over x squared, of which 1 over x squared can be expressed as x to the power negative 2. So the integral of this is negative 1 over x. So this is what we'll actually get when we integrate this value. So we have negative 1 over x. So now from integrating by parts, we're going to substitute in the values. So we know that u is ln x and then v is negative 1 over x. So we multiply the two and we'll have negative 1 over x ln x minus the integral of, remember that v is negative 1 over x times du dx is 1 over x. So we have it right there. So this is what we have. But now this minus and this minus will affect each other. Then we can actually see that 1 over x times 1 over x is 1 over x squared. So now we're left with the integral of 1 over x squared right there. So this is what we have. And then this becomes a plus. Now the integral of this, we can actually still find it. We know that 1 over x squared can be expressed as x to the power negative 2, of which we again have negative 1 over x right there. So now when we open the brackets, we can actually see that now this plus will become a minus. So we have negative 1 over x ln x minus 1 over x plus c, and this is our answer. So next question is a question from UNEB 2018, and this was question number 3. So we're being told to find the integral of x squared ex dx. Alright, so this is another easy one. But as I can see, the good thing here is every single value is actually easy to both differentiate and integrate. So in this case, you can choose any and it will actually still be okay. So you can let any value be u and you can let any value be dv dx. So let's choose this. So I've chosen to make my u to be equal to x squared, and I've chosen to have dv dx to be equal to ex. Now what I know is that the derivative of x squared shall be equal to, so I have du dx being equal to 2x, and then the integral of this, if I want to find v, I'll have to find the integral of ex, of which the integral is just going to be equal to ex, so v shall be equal to ex. Then integrating by parts, we're going to put everything back into the formula, and then I'll have, because you know what u and v are, so v is ex and then u is x squared, so multiply the two and we'll have x squared ex minus the integral of v is ex times du dx is 2x, so multiply the 2 dx, as you can see. So now I'll have x squared ex minus, I can pull out the 2 from here, minus 2 into the integral of x e power x dx. Alright, so now this is the next step. Now next I actually have to solve for this value right there. Alright, so next we actually have to solve for this integral right here. But what we can actually see is this integral right here will also require integration by parts. How strange, right? This is an example of a number that requires integration by parts more than once. So we're also going to consider this integral right here, and we're also going to integrate it by parts. So let's consider that integral. So for 2 into the integral of x ex dx, so let's integrate that. So this also needs to be integrated by parts. So therefore we're going to let u to be equal to x, and we're going to let dv dx be equal to ex. So you can say that du dx shall be equal to 1, and then v, to find v, we're going to have to integrate ex, of which v shall be equal to ex. And then therefore, integrating by parts, putting that in the formula, this is what we have. So 2 into the integral of x ex dx shall be equal to 2 into x ex minus the integral of ex times 1 dx plus c. So what do we get? So here we'll be left with the integral of ex dx plus c. Now the integral of ex is easy. That's basically going to be equal to ex. But remember that we have these 2 outside, so we're going to multiply the 2 in, and we'll have 2x ex minus 2ex plus c. So therefore the final integral becomes this. So now we're going to substitute all this back into the initial integral. So we'll have the integral of x squared ex dx being equal to x squared ex minus what we actually have right here. So therefore when we open these brackets, we'll have a minus sign here, and then this will become a plus. So we'll have x squared ex minus 2x ex plus 2ex plus c as our final answer. Alright, so question number 9. So we're being told to find the integral of e power 2x sine x dx. So these are actually also 2 functions. So this will actually also require integrating by parts, because you can see that u substitution won't work, and clearly integrating by parts will not, trigonometric substitution will not work in this case. So we're going to use integration by parts. So this is what we have. So we're going to let, so these are also both easy, so you can let any value to be whatever. So we're going to choose, but I've chosen to make u to be equal to sine x, and then I've chosen to have dv dx being equal to the e2x. So now if I differentiate sine 2x, I'll have du dx being equal to cos x, and then if I choose to integrate this to find v shall be equal to the integral of e2x dx, of which when I integrate this, I'll have e2x over 2. So this is what I get as the integral of e2x. So integrating by parts, this is the formula, and then what I'm going to do is I'm substituting everything into the formula, and then I'll have e2x over 2 sine x minus the integral of e2x over 2 times cos x dx. So this is what I actually get right there. So therefore I can say that I can pull out a half from here, and then I'll be left with the integral of e2x cos x dx. But as I can already see, this actually also needs to be integrated further. So as you can see, this will also require to be integrated by parts. So this requires double integration by parts. So let's consider this section here alone. So let's consider a half into the integral of e2x cos x dx. So I'm going to let u to be equal to cos x, and I'm going to let dv dx to be equal to e to x. So when I differentiate this, I'll have du dx being equal to negative sine x, and then as you can see, to find v, I'll actually have to integrate this e2x, of which v shall be equal to e2x over 2. So integrating that by parts, I'm going to have this value right here. So remember, we have a half outside, so it's going to be a half into e2x over 2 cos x minus the integral of e2x over 2 times negative sine x dx. So when I solve that, I will have it being equal to a half into the integral of e2x over 2 cos x plus a half into the integral of, because I can pull out a half from here, then I can say this negative sign will affect this negative sign and I'll have a positive, so this will be into the integral of e2x sine x dx. So we can now see that the integral, this integral right here, the integral of e2x sine x dx is the same as the original integral. So we're going to stop here. So we shall now have the integral of the original integral, which was e2x sine x dx, shall be equal to e2x over 2 sine x minus. So now we're going to bring in what we've actually just found right here. So we're going to substitute that in minus this value right here. So now that we have that, let's open the brackets. Then we can say that we'll have e2x over 2 sine x. Now this a half times this, so 2 times 2 is going to be 4. So we have minus e2x over 4 cos x. But remember, we have a minus sign here, so it will affect this plus, and this will also become a negative. Now a half times a half is also going to be a quarter. So a quarter into the integral of e2x sine x dx. So as you can see here, we now have like terms. Like I said, we've seen that this is the same as the original. So now this and this, we're going to combine this with the original value right there. So we're going to do a collecting of like terms. So, alright, so when you collect like terms, it means we shall take this value here, the quarter integral of e2x sine x dx, we shall take this value to the left hand side. So when we add this to this value, because this shall become a plus on this other side of the cosine, when we add them, we shall have 5 over 4 e2x sine x dx. So therefore, after we collect like terms, this is what we end up having. So we have 5 over 4 into the integral of e2x sine x dx being equal to e2x over 2 sine x minus e2x over 4 cos x. And therefore, remember, still we need to make this the subject. So we'll have this being the integral of e2x sine x dx being equal to 4 over 5 into a half e2x sine x minus a quarter e2x cos x. So as you can see, we can actually still, for now, I'm going to multiply this 4 inside. So when I multiply the 4 inside, I'll leave 1 over 5 outside, and I multiply 4 inside, this will reduce, and I'll have 2 e2x sine x minus, this will become e2x cos x. And then this shall be our final answer. Alright, so another question. So this is a question from UNEB 1995. This was question 9.2. Now we're going to look at an example where integrating by parts is simply just a step. So we're being told to find the integral of 3 to the power root of 2x minus 1 dx. So what are we going to do in this case? So let's solve it. So the integral of this, as you can see, this number will first require us to first use u substitution. But as I've mentioned before, that u substitution can be used with any letter. But remember that we can use any letter. Now, because in this case, there's actually going to be an integration by parts later on, I'll use a different letter than u to do the substitution methods. So I'm going to let t to be equal to root of 2x minus 1. Then, as you can see, this is the same as putting that to the power a half, and then therefore dt dx shall be equal to, so if I differentiate this, I can say that I need to use chain rule. So when I differentiate this, I will have 1 over 2x minus 1 to the power a half. Then therefore we can say that dx shall be equal to 2x minus 1 to the power a half. So this is what I get. So therefore I can substitute that back right here. Remember that we had let the power to be actually equal to t. Alright, but we shall remember that t is actually equal to 2x minus 1 to the power a half. So that means we're going to replace this with a t. So that's going to be important to remember. So we'll have integral of 3 to the power t times t dt. So this is what we end up with. Now when we have it in this part like this, you can actually clearly see that now this will now require integration by parts as we continue. So you can now integrate by parts. So integrating by parts, we're going to let u to be equal to t, and we're going to let dv dx be equal to 3 to the power t. So what happens is when we differentiate u, we shall actually say that we have du dt being equal to 1, and then here to find v, remember we're going to integrate 3 to the power t, of which our v shall now be equal to 3 to the power t over ln 3. So this is going to be a knowledge that's very important. So we learned this from the video on exponential integrals of exponential and logarithmic functions. So now integrating by parts, this is the formula. So we're going to substitute in the values, and we'll have 3 to the power t times t over ln 3, because we're multiplying the u and the v, minus the integral of, so where there is v is 3 to the power t over ln 3 times 1, of which du dt is 1 dt. Then this is what we end up having. So I can actually pull out 1 over ln 3, because that is a constant, into the integral of 3 to the power t dt. Alright, so now basically the integral of 3 to the power t shall be equal to, we shall have 3 to the power t over ln 3, and then we'll have this plus c, because we've actually integrated this side. Now as you can see, when I multiply this to this, I'll have ln 3 squared, and then 3t shall be at the 3 power t shall be at the numerator. Then I can say that I can actually factorize out a 3 to the power t over ln 3, and then inside I'll be left with t minus 1 over ln 3, and then plus c. But remember, t is actually a root of 2x minus 1, so therefore this means that we'll have 3 to the power 2x minus 1 over ln 3 times bracket 2x root 2x minus 1 minus 1 over ln 3 close bracket plus c. So this is therefore our final answer, as you can see right there. Alright, so now that we've accomplished much and we've learned some few examples, I encourage you to try these numbers out using the knowledge of integration by parts. So just basically try them out and compare your answers to the answer that I've actually placed on the right hand side of each one. Because I believe that answer, after you've done these and tried them out, you will actually now have a better understanding of integration by parts. So these are just a few numbers, and I believe that after you try these out, you'll actually be good in your knowledge of integration by parts. Thank you so much for watching. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.